recording. And let's talk about Maxwell's equations and Coulomb's law. Okay, we're in chapter 4 now. This is where we're gonna do most of chapter 4. We're gonna also get into chapter 5. We won't do all of chapter 5.
Can you share your screen, Professor?
Oh, thank you. Yes, I forgot to share my screen. Someone just brought it up. I thought I shared the screen earlier, but I guess I did not. All right, there you go. Let me know if you can't see it, okay? All right. Great, thanks. So Maxwell's equations. Maxwell was a guy. His first two names, I guess, were James Clerk. He was born in Scotland. He was a pretty incredible guy who, as we were talking about at the beginning of this, doesn't tend to get the at least popular recognition kind of that he probably deserves. Among scientists, he does, though. Among scientists, they really speak highly of him. In fact, Einstein, at one point, he's always said many complimentary things about Maxwell. At one point, he was getting introduced, doing some talk, and someone said, made a comment that Einstein stood on the shoulders of Newton, right? That's a typical thing that someone might say. And Einstein said, no, I stood on the shoulders of James Clerk Maxwell. Okay, so to give you an idea of Einstein saying that, right? So Maxwell didn't come up with all of the equations in Maxwell's equations himself. He put them together and added a little bit of special sauce to it, okay? So here's some names that you'll recognize: Coulomb, Gauss, Ampere, Faraday. These people all had come up with their own equations, and he kind of put them together, okay? So he was born in 1831, and he did this in 1873. So he's 42. Okay, I'm 42. That's so. I was saying the other class too, it's disappointing when you hear how old some of these scientists were when they made their major discoveries, right? And he died at 48. He died at 48. You had no time to waste. He had cancer. you had to do it quick. Well, in his case, he had cancer. He had abdominal cancer. It was the same cancer his mother had, and back then they didn't have much for treatment for that. It was pretty much game over, I think. And he made a lot of breakthroughs in the 1860s when he was in his mid-30s and that sort of thing that are like, pretty remarkable. So let's talk about what he did. He came up with these set of equations that unified all classical electromagnetic theory. Now, these days in physics, they talk about quantum field theory and that sort of thing, and that's kind of another level when you get down to that extremely small scale. But as far as we're concerned, as kind of electrical engineers at more of a macro scale, his equations cover all electromagnetic theory and really underlie, like, let's say your circuits courses, 240, 340, all that stuff. All of those are all just simplifications ultimately of Maxwell's equations, right? It would be ridiculous though to use Maxwell's equations to solve those circuit problems, okay? So basically voltages, currents, all of that are abstractions. The Kirchhoff's voltage law, current law, we're actually going to see a more generic version of those, but all of that are all approximations. You're in a regime where you can use a much simpler form of the equations. You don't need the complex Maxwell's equations to do it, but really underlying everything are these equations. So they're super, super fundamental. They hold in any material, including free space. And this is partly what makes it complicated, less so for us. But look at this. This is E for electric field. Depends on X, Y, and Z. It's a three-dimensional thing, right? Fields exist in 3D space, and they can vary with time. So we're talking about a vector that's a function of 4 variables. So it can get a little complicated, right? So let's do it. Let's talk about the equations. You've probably seen them before in some places, but maybe you might struggle right now if I put you on the spot and I said, describe what these equations mean. So let's talk about it. There's also different forms of the equations. You might have seen Maxwell's equations with integral signs. There's differential forms of Maxwell's equations, and there's the integral form. This is the differential form. Let's define our variables first. E, electric field intensity. It has units of volts per meter. Okay. D, electric flux density, has units of coulombs per meter squared. There's a simple relationship between D and E. It's just proportional to this thing epsilon. That is the same epsilon we've been using all semester. What's a formula you know for epsilon? Probably the only formula you know for epsilon. Okay, and what's E naught? What's its value? Yes, yeah, that's right. Yep. So we know epsilon naught. Epsilon R changes based on what material you're dealing with. If it's air, epsilon R is 1. If it's distilled water, epsilon R is 81 or something like that. So that means D and E for that case would just vary by 81 times 8.854 times 10 to the minus 12. D, E, just different by some number you punch to your calculator and multiply that one by. So don't get caught up in the D's and E's, and because it sounds complicated when you have electric field intensity and electric flux density and you're saying all these things, it sounds complicated. Just think of D and E as the electric field, the electric field stuff. I'll just say electric field, okay? Because we could have written all of these equations in either E or D. For instance, if we wanted to write this in terms of E, we would just sub in epsilon times E. Now we got rid of all the D's, right? We could do the same thing down here. Yeah.
So when it comes to
yes, yes, yep.
Is that mostly the main component in that equation that would alter the density?
Yeah. So this is a density, and if you doubled your epsilon R, the magnitude of D would double. So it is like a density.
So
yep. And the units are coulombs per meter squared. So if you doubled that, you could kind of think about that in terms of its charge per meter squared would be, say, double, something like that. Okay. Okay. E and D, electric field stuff. H and B, the equivalent, but for the magnetic world. H is the magnetic field intensity, like E. It has units of amps per meter. B is the magnetic flux density, like the D. Look, we've got our simple relationship between them, just like for D and E. Mu equals mu R times mu naught. What's mu naught? Yep, that is right. So bottom line here is we know mu naught and we know epsilon naught. The only thing that changes is the epsilon R or the mu R, and those depend on the materials in which the fields exist. So that's all. Like, what material are the fields inside? Are they in water? Are they in wood? Are they in plastic? Are they in air? Right? Each one of those would have a specific epsilon R that's associated with it, and then it would just scale the E or the H based on that epsilon R or mu R. So there's nothing special about it. I'll just kind of refer to the H and the B as just the magnetic field. Okay. Again, we could replace all the H's with B's or the B's with H's. It's just a scaling factor. Yep, they mean something different. It's the ones taking into account the material properties and is more of a density. This one has units of Webers per meter squared, which is also a Tesla, named after Nikola Tesla. Okay, so we've kind of checked off the D, the E, the B, the H. All we're left with are the rho V. It's a rho, not a P. Rho V and J. Rho V, note that it's not bolded, so it's not a vector. Note that the D, the E, the B, the H, they're all vectors. Okay. Rho V is the electric charge density per unit volume. So it's a charge density. The V is for volume. So the units are coulombs for charge per meter cubed. Last one is a J. That J is bolded. That means it has a direction. It's a current. So it's really what direction is the current flowing in? And it's a current density, which just means it's amps per meter squared. All right, let's try to make some sense out of these now that we've defined everything. Okay, I think I got all the units for everything, right? Okay. Okay, let's make some sense out of this so that you could walk away from here and you could at least give a bit of a feeling to someone else what Maxwell's equations mean. Okay. The way that if you really wanted to learn it, it'd be great to try to actually program it in MATLAB or something like that. You really learn it then, but that's going to take quite a while. We just want to be able to give you a feel. I just want to give you a feel for what they all mean. Okay, someone say the top equation in words. Nope, I don't like that. I do not like that at all. There you go. I like that a lot more. The divergence of, yeah, the divergence of D or the divergence of the electric flux density equals the volume charge density. Okay. Then you say, well, what is the volume charge density? Well, we're going to talk more about that. But for now, think about it's units, coulombs per meter cubed. Let's say you had a box, you had a bunch of point charges in the box. Those point charges have some charge, that's in coulombs. And so if you knew kind of how much charge was in the box and you divide it by the volume of the box, it's kind of coulombs per meter cubed. It's kind of like how much charge is there in that volume, okay? And think about it being a really small volume, like approaching a point. Okay, so divergence. Anyone remember what we talked about when we talked about divergence, how to think about it, like what it physically means? Yeah, yeah, exactly. It's like a source or a sink. So we're talking about sources of electric field lines or sinks of electric fields. That's the left-hand side. It equals something, rho V. If rho V equaled 0, there would be no source, no sink. The divergence would equal 0. If there's no source and no sink, there's no generation of electric fields. There's no sinking of electric fields, which kind of makes sense because there's no charge, right? If you had a single point charge though, in a little tiny volume box or something, right? That would be a non-zero coulombs per meter cubed. So the right-hand side would not be 0. So the left-hand side says there would be a source or a sink. If it's a positive value, if it's a positive rho V, on the right-hand side, you have a positive non-zero number. That is a positive divergence. A positive divergence means it acts as a source of field lines. So it's kind of telling you that, if you want to think about it this way, that rho V, that charge in that volume, is producing electric field lines that diverge away from that point source, if you want to think about it that way. Okay, that's all that one says. No. Did you say just like a magnet?
Well,
let's go down to the third one. B is the magnetic field thing. So interpret that for me. What's that? What does that mean? Yes. There's no like generation or it's not altering it, right? There's no like generation of it or sinking of it where it kind of goes away or anything like that, right? Then you think, well, what does that mean? You could kind of think about it that way. The way I think is easiest to think about it is, you know how we can have a point charge in the electric field? We can have like a plus Q. And from that plus Q, that would correspond to a positive rho V. And that means it is a source of field lines. There is no equivalent to that with magnetic field stuff. The fancy way to say that is there is no such thing as magnetic monopoles, because a single positive point charge, you could call that a monopole. And if you had a negative point charge, that would also be a monopole. And if you put them together, it would be a dipole, okay? All magnetic stuff has the two poles, like a north and south magnet, north and south pole on the magnet. You can't just get the north or just the south. What does this mean? Well, if a positive is always associated with the negative, all the fields are always in loops. No one's discovered one yet. Sometimes there's things like magnetic charges that are used as a mathematical convenience, even though they have not physically been discovered. But anywhere you read it, it normally accompanies the description of this with saying, magnetic monopoles have not been discovered yet. Who knows, right? Yeah, so there's two ways. There's like, we're going to use it as a mathematical convenience. That's the one kind of conclusion. And the other thing is when they say it hasn't been discovered yet, meaning it could be. It just hasn't been discovered yet, okay? So what does that mean if you have a bar magnet and it's got like, it's painted red on one half and it's like, I don't know, silver or something the other half, and you're like, I'm going to break it in half, right? And get my north and get my south. No, now you've got two magnets, both with the north and the south on them, okay? Right, exactly. So all the fields are in loops. There's no generation or sinking of the fields, no matter what. That's what this one means. Okay, those are the two divergence equations. Now, probably the more interesting ones and the ones that are a little bit more difficult to maybe visualize are the other two. Someone say in words the second equation. Equal. And rather than say that, exactly, rather than just a generic partial of this with respect to this, it's really telling you how the B field, how the magnetic field is changing with time. What if it's not changing with time? What's the right-hand side of that equation? And so the left-hand side of the equation means the curl of the electric field has to equal 0, which means it's not curling. It's a 0 vector, kind of doesn't mean anything because its magnitude is 0. So it's like it's just 0. It's like it doesn't exist. Think about it that way. Yeah.
I'm just saying because like that the curl defines the.
Yes, you're right. No, you're right. Yeah. In this case, it's just 0 though. So it's like, whatever.
I had a math professor that would
be very picky about that. It'd be like 0 with like a line or something. Yep. Okay. So if it's 0, if the magnetic field does not change with time, then when you take the derivative of it, with respect to time, it equals 0. That means there's no curl. The curl of the electric field 0. Okay. Now let's say the magnetic field does change with time. How would you get a magnetic field that changes with time? Give me some ideas. AC voltage corresponding with an AC current. The AC current is a time-varying current. The time-varying current is going to be, come along for the ride, is going to be a time-varying voltage, or you could say that vice versa, right? Okay, you could have physical movement, or you could have current changing with time. For those of you who go on and study in 571, the follow-on course, or if you do the independent study in like chapter 6, that's what you would be looking at. Okay.
Yeah, I'm gonna go my spot.
Oh, 6.3. Do you remember what that one is? Okay. So right around 6.3, it's like time varying currents and physically moving, like spinning things and that sort of thing, right? Yeah, exactly. Yeah. Okay. So let's say we had time varying current, right? We plug something in the wall at 60 Hertz AC. It's having a time changing current. So there is a time changing magnetic field. B is changing with time. That means the right-hand side of that equation, the negative time derivative of B is not equal to 0. That's interesting. Because if it doesn't equal 0, the left-hand side of that equation has to equal it, right? Like this has been fully verified. This equation has to hold. That means the left-hand side does not equal 0. That means there is an electric field, number 1, which by itself is kind of mind-blowing or weird, right? Because all you did was you made a time-varying current, and associated with that was a time-varying magnetic field. But that equation says there also has to be an electric field. It has to obey that equation. The curl of it has to equal the time rate of change. The electric field is going to be time changing as well if the magnetic field is time changing. And so, well, you know, he was my age when he figured them all. Actually, this one I think is this is Faraday's equation. This one's Faraday's. So it's Gauss, Faraday. This one doesn't really have a name. It's sometimes called Gauss's law for magnetism. This one's Ampere's law. So these existed. He sprinkled this special sauce. The special sauce is this term right there that we'll get to.
I guess I'm just not on that because when you said it's Faraday's and looking at the time for Faraday.
Yep.
He didn't finish school to do something like that, but he did have some apprentice, I guess, there that did it for him. That's what I was.
Oh, really?
Yeah.
Like there's some kind of controversy about
No,
whether.
no.
Are you trying to steal Faraday's thunder here?
No. I just hear different stories. That's
Okay.
all.
All right. We got conspiracy theories from Anthony about Faraday. Okay. So think about what that means. If ever we have a time-changing magnetic field, there is an associated electric field in a Bayes' equation. Bottom equation. Let's ignore the J for a second. Okay, let's say the J equals 0. In free space, the J equals 0 because there's no, like especially if you think of outer space, electromagnetic waves clearly travel through outer space, right? Or we want to get the light from the sun, right? There's no atoms there. So the way you normally think of a current is it's atoms, or it's electrons moving from atom to atom, right? But if there are no atoms, then it's like, how does this work, right? It's kind of confusing. In that case, J would equal 0 because that is a current density. It's amps per meter squared. In outer space, J equals 0, okay? Let's assume that for a second. And we just have the curl of H, the curl of the magnetic field, equals the time rate of change of D with respect to T. So now if somehow we had a time varying electric field, that is going to be associated with a non-zero magnetic field. Same thing as we said before, right? If you created that somehow, how would you create that? If you could move charges around, if you physically move charges, and with respect to time, that would be non-zero. There has to be a magnetic field associated with it. So the way electromagnetic waves propagate is if you have some source, like a time varying current, right? That creates a time varying magnetic field. That means this side of the equation is non-zero, means there has to be an E field. The E field has to obey this curl equation. The E field is also going to be time varying if the B field is time varying, which results in this being non-zero. And then this equation has to hold where the curl of H has to be equal to that. And now you've got a time varying H field, which comes back up here, and a non-zero derivative, which then has to be associated with D. So you can think about it like you have a time changing H, and that is accompanied by or associated with or generates an electric field. And then that electric field is accompanied with or generates a magnetic field, and they kind of regenerate each other. And this is how electromagnetic waves propagate. Yeah. And so they're all together, right? Like you often see these plots where maybe one's going this way and the other one's going this way. They're at right angles to each other. You cover that a lot if you take 571. And so that covers that. This is just current density. That's what you normally think about as current, okay? And we know that if nothing's changing with time, meaning like DC current, right? DC current, and let's say the electric field's not changing with time, that's gone. But the magnetic field is not zero, right? Because if we have a DC current, our J is not zero. So that means our H is not zero, okay? But H won't be changing with time. So this derivative will be 0 and the E field will be 0. Okay. So what did Maxwell do? He put all these together because these were just totally separate equations. Okay. He put them together and he added this term. And this term is what couples them together, right? Because without this, then yeah, okay, the E field depends on the B, but the H does not depend on the E. The H is independent from it. But with this coupling, now you get that behavior where the one's accompanied with the other and they kind of go back and forth, right? So this here is called the displacement current term, and it's a weird one. We'll, 571, you talk more about that, okay? We won't talk about it too much here because we are gonna let things not vary with time. But this is a weird one because think about this. This is an electric field thing. If we take the time derivative of it, somehow it's like, remember the units of this are amps per meter squared. To add these together, the units of that has to be amps per meter squared. How on earth can a time derivative of an electric field have units of amps per meter squared? It's a bit of a weird thing, but it really is the magic there. And if you get down to like, how does current go through capacitors and that sort of thing? Like if you had capacitors that are parallel plates that really are a vacuum in between, then you go, wait a second here. Okay, and the wire, I have current traveling, which is electrons hopping from atom to atom to atom. But then I hit this plate, one side of the plate, right, in your circuit world. And if you really pumped out all of the air and everything in between there, and there were literally no atoms between the plates, how on earth can that current get to the other side, right? It can do it because of this displacement current term here. And that's one of the things that maybe you could choose that section if you wanted to, or look at it for the independent study if you wanted to look at that one.
That's where they create a surface.
Yep.
Right? And they create a paraboloid, and then all of the curls cancel except for the amp, and then get a magnetic field to there.
Kind of, I think. It's actually simpler than that for this simple capacitor thing, but I think I know where you're at there. Yep. Yeah. Okay, so hopefully that gives you a bit of a feel for how these equations work. To get into the real details, well, you kind of got to actually get into playing with the equations and that sort of thing. Any questions about these? Yeah. No, this whole term's the displacement term. That's still partial. It's still partial derivative with respect to t. It's just that whole term is called the displacement current term. Definitely could. Yep. You could replace all the d's with the epsilon e, and yep, you could do that. All right, so we are not going to let things change with time. It's going to make our life a lot easier. All right, let's go back and figure out what would happen. Well, we already said if nothing changes with time, that means that doesn't change with time, which makes that equal to 0. It also means that doesn't change with time, and that equals 0. So now look what happened to our equations here. Our electric field stuff is just totally isolated from our magnetic field stuff. If things change with time, you can't just look at, one or the other. You need to deal with both, right? Because if you want to look at the magnetic field, well, it depends on what the electric field's doing. If you want to look at the electric field, well, it depends on what the magnetic field's doing. But if nothing's changing with time, now the coupling is gone. Now they're just 2 electric field equations, 2 magnetic field equations. So that's what we're going to do. And so let's simplify that. So then you might say, well, when does that happen? Like, is this a practical thing? Is this kind of useless? Like, when are you in the static state? And the first one is when charges are just fixed in space. So they're not moving with time. The other one is when charges are moving, but they're moving at a steady rate. What does that mean? It means DC current. So we're just not dealing with AC stuff, okay? So rho V isn't changing with time and J isn't changing with time. Okay, so what do we got? So we got 2 things. One's called electrostatics, and the other is called magneto. Electrostatics, because it's electric field stuff, and static as in static with respect to time. It's not changing in time. So we have our first equation. It doesn't change. It had nothing to do with time, right? It doesn't have any time derivatives or anything like that in it. The second one is the one where the curl of E now equals 0. Magnetostatics, our first one, our no magnetic monopole one is the same. It's got nothing to do with time derivatives. But our curl of H now equals J. I'll go back here just for a second, just so you can see we still have the J. The J isn't changing with time, but it's still there. All right. So what's it used for? It's used all over the place. Touch screens, like on your iPad, your phones, LCDs, transistors. Anybody in 340 right now or has already taken 340? Are you in the middle of MOSFETs? MOSFET amplifiers? What does MOSFET stand for? Yes. The field effect transistor part is because of the electric field. If you remember how the MOSFET works, you apply a gate voltage, like a VGS, let's say, and that positive gate voltage essentially attracts the negative charge carriers underneath the gate. That's by an electric field. And then if you apply a VDS, that's really an electric field from the drain to the source, which can push those one way or the other. So it's called that because it's an electric field effect. It's completely based on that. Which of course, MOSFETs, you can have NMOS and PMOS, and NMOS and PMOS is really CMOS, complementary metal oxide semiconductor. And every one of your computers and phones, the processor in it is a CMOS processor. So kind of at the bottom of all of that is still electromagnetics, okay? We got micro electromechanical switches like the accelerometers in your phones and in your airbags, capacitors, defibrillators, electrocardiograms. It's got tons of applications, even though we're not letting things change with time. Okay, so let's get into the weeds a little bit more. And the first thing we want to talk about is that rho v. Because we're dealing with electrostatics, we've only got the two equations, right? We got the divergence of D equals rho v, and we got the curl of E equals 0. Okay, so we want to talk about what is this rho v, and what it really is it is a charge distribution, so coulombs per something. If it's a volume, then it's coulombs per meter cubed. If it's a surface, it's coulombs per meter squared. If it's a line, it's coulombs per meter. It's how are the charges distributed over this line, surface, or volume. Here's our definition of rho v. Volume charge density. So rho is going to be charge density. Look to the subscript to determine if it's a volume charge density, a surface charge density, or a line charge density. We've got, remember I said you got some charge inside of a cube or something, right? So you got coulombs per meter cubed. Well, that's what we have here. Some charge in some volume, but we're going to let the volume go to 0. And if you were really picky, you would say, hang on, if we really let the volume go to 0, then there'll be nothing inside, right? Because atoms are discrete things. So you got an atom, it's got an electron cloud, it's got a nucleus, there's the neutron, there's protons. And if you zoomed in enough, you know, you'd have to get pretty crazy. But if you took this literally, delta V goes to 0, you'd be in like the spaces between the atoms or something. There'd be nothing in it. There'd be no charge. There'd be no Q. There'd be nothing. Yep. We're electrical engineers. We are way, way away from that level. All right. We're dealing in the, you know, usually like the human scale thing. If you wanted to get down to that, you'd have to take all kinds of quantum, field theory effects into consideration, all that kind of stuff. So basically, for our purposes, we're getting away with this definition, even though technically it's not quite right. At the scale we're operating at, it doesn't make a difference, okay? Okay, so rho v equals dq dv. We could rearrange this equation for dq. So let's say we solved it for dq. It would just be rho v dv. What does that mean? Some differential amount of charge equals the volume charge density times some differential volume. You can probably guess where this is heading when we have these dq's and dv's. If we took the integral of both sides, well, the integral of dq, well, it's going to give us the overall charge q. And on the right-hand side, the way you can interpret that is for all the dv's that make up the volume v, we're essentially multiplying the rho v at that point times the dv, and we're doing that for all the dv's that make up the overall volume, and that's how you get the total charge. So here you go. Our total charge is called q, volume integral rho v dv. That's if you have a volume charge distribution. If you have a line charge, see, it's rho L. We do much the same thing. Rather than let delta V go to 0, we let delta L go to 0. Rho S is for a surface charge density. We're letting delta S go to 0. At the end of the day here, if we do the same thing though, and we solve for dq, we get rho L dl. So we could get q equals the integral over the line of rho L dl. If we solve for dq for the bottom one, we get rho S ds. And that would lead to q, our total charge over the surface, is the surface integral rho S ds. So basically, these are different ways that the charges can be distributed. You determine, is it a line, is it a surface, is it a volume? And if you're trying to figure out what the total charge on that line, surface, or volume are, you use one of these three equations. So probably what we'll do for the rest of today is do a line charge example, do a surface charge example, and do a volume charge example. Okay, that'll probably take us the next 20 minutes or so. So let's start with the simpler one here. We want to start with the line charge example. And so we want to find the total charge. Okay. In a 10 centimeter long cylindrical tube oriented along the z-axis, the line charge density is rho L equals 2z, where z is the distance in meters from the bottom end of the tube. There's some potential confusion in this. Confusion number one, or maybe the primary confusion, is that picture and the description look like a cylinder. A cylinder is a volume, but then it gives us a rho L, and it calls it a line charge density. So if you were reading this, you'd go like, wait a second here, what's going on? Is this a volume, or is this a line? And the answer is, it's a line. Just think about the cylinder as being extremely tiny, like the radius is being super, super small, okay? It's just drawn this way so you can actually see like the green dots representing the charge distribution in it.
I'm gonna say, 'cause the line itself is the shape of the zone.
Yeah, and if you drew it as a line, it would be a line that perfectly aligned with the z-axis, and then it'd be confusing for the drawing. But this would be a totally fair question if you were given something like this on an exam, to say, I just want to make sure I got this right here. Like, it's just like kind of an infinitely thin cylinder, right? You know, I'd be like, yeah. So that's the first thing. It is a line. Think of it as a line. Okay. It's 10 centimeters tall. The bottom of it looks like it's at the origin, like right in the XY plane, like it's z equals 0. We want to find the total charge. We're given this rho L. It doesn't give it in units, but you can assume that we're in the normal units, coulombs and meters and seconds and all that kind of stuff, right? So Z would be normally in meters. Rho L, what would the units of rho L be? Coulombs per meter. And what units do you think our final answer is going to be in? Coulombs, because it's a total charge. If this line charge was distributed uniformly over this line, we wouldn't need to use calculus. We could just like multiply and we'd be done, right? It'd be like, if the line was 10 centimeters long and we had a uniform charge distribution of like rho L equals 2 or something, 2 coulombs per meter squared, or coulombs per meter, sorry, because we're a line, we would just multiply that by the length of it and we'd be done. The reason we have to use calculus is because it varies across it. So we need to slice this thing up into little pieces and do our usual calculus stuff. So we're gonna like slice this up into little DLs, okay? What would the charge be like right down at 0? What do you think it would be there? And what makes you say that? Z is 0, that's it. Try to get an idea of what these things look like from this. I would look at that and I'd go, okay, I have nothing there. As I go up, this increases. I'm at a peak up there. This is why we have to split it up, because the charge is different for each one of these DLs, okay? So we recognize that it's a line charge. We want the total charge on the line. We could come back here and say, all right, this is our formula for the line charge. So we have Q, our total charge, equals integral of rho L dl over the line L. We're given rho L, so that's good. What is dl? It's dz. Our line is oriented along the z-axis. So a lot of the challenge of this part of the class, you have to set it up. You have to set up the problem, okay? It's not like your previous calculus classes where you're just given the integral and you got to solve it. Here you have to think about it. If you left it as dl, like if you just plugged in the rho L, you said 2z dl, like what's dl? Like how do I deal with it? I got a z, I've got a dl. It doesn't really make sense. Like you got to get it all in terms of, you know, in this case, the Cartesian coordinate system, coordinate variables, okay? dl equals dz because our line is oriented along the z-axis. And if we split this up into little pieces, each one of those little pieces is a dz. If the line was along the x-axis, it'd be dx, okay? Okay, so we've got an integral. Our rho L is 2z. Our dl is dz. What are our limits of integration? It should be in meters. Yeah, so 0.1, okay? Okay, can someone do that integral? I bet you like that integral. Oh, you already did a whole thing. Okay, that's good. So z squared, and then we evaluate it from 0 to 0.1. So it's 0.1 squared minus 0 squared, and it's 0.01. And as we said, the units would be coulombs. Okay, so 2z, the antiderivative of it, z squared, we need to evaluate it from 0 to 0.1. We plug in that value first and subtract it from the bottom value plugged in. That's the first one. Not too bad, right? This one's not too bad either. None of these are too bad. We're still kind of warming up the calculus. What's that? Oh, okay. So it's always a good idea to try to get an idea of what the problem is. And if you can draw it, draw it. I can draw this one. I can't really draw the next one. It's going to be a little messy, but even if it's a little messy, it may help you understand things. We have a square plate. There's my square plate. I'm going to draw my coordinate system. You can see the plate's defined by the x's between -3 and 3 and the y's between -3 and 3. That's another way of kind of saying the plate is centered in the xy plane. Okay. So we have the coordinate system being something like that. Okay, where this well, let's call the square plate is in the XY plane. That means I'll call that Z. Does it matter which is X and which is Y?
It's easier to follow.
It matters because of the X hat cross Y hat has to equal Z hat. Yep. It's just a difference of, in this case, it wouldn't really matter because it doesn't matter which Z is up or down, right? But in other cases, it will matter. And so which would it be if I drew Z like this, which would be X and which would be Y? So who votes for this being X? Okay, anybody vote for that being X? No, okay, so it's this one because you put your right hand, extend your fingers out in the direction of that, curl them towards the other one, the thumb goes up in the positive Z direction. So this is X, that's Y. Not, again, for this particular problem, it doesn't matter, but for other ones, it could. Now, the plate goes out to 3 on the Y, and it goes to -3 as well, so that's -3. Goes out to 3 on the X, and -3 as well. So there's our setup. Now what are we going to do? Well, whenever we do these things, we got to break up our surface into little chunks. Okay. We'd recognize that it's a surface charge and we're trying to calculate the total charge. So we'd have to use that one. Q equals integral over the surface of rho s ds, where each one of those squares down there at the bottom right is a ds. So basically we're saying each one of those squares, we're going to multiply by the rho s at that location and get the contribution, the total charge for that square. Then we'll go to the next square. We'll add them all up or integrate them. So we got to translate this. What would ds be? Yes. Yep, doesn't matter. So each one of these little squares, that is the area. Note that if you're doing length times width, and the one is along the X and the other is along the Y, that's why it's dx times dy. We're given rho s. So this is an integral. It's a surface, so it's a double integral, okay? So we've got a double integral. Rho s is given to us as 4y squared, and we just said our ds is dx dy. Okay. Yep. You just need to, it doesn't matter what order you write it in, you just need to be careful about your limits of integration and which one applies to which. In this case, they're the same, so it doesn't matter. Yeah. So what would the limits of integration be? Yes. Basically, we want to cover the whole plate. The plate goes from -3 to 3 in the X and -3 to 3 in the Y. So I'm just going to say -3 to 3. Say that again. Oh. Yes, the only thing you got to look out for is just make sure that you take this into account because it's changing with Y. And so for instance, if you like cut off, and it could be this is an even function, so it might be okay, but it could be different in a different case. So yeah. Yes, yeah. What would the surface charge be like right along here, like right along the x-axis? Yep, because y equals 0 along x. Okay, think about y. It's 3 here, it's maybe 2, it's maybe 1, it's 0 here, and 0 goes all the way across there. And so it'd be 4 times 0 squared at that point. Okay, so let's say then I told you what the rho s was right there. And I said that point's kind of in the middle of that quadrant. And so it's kind of like minus 1.5x and minus 1.5y. And then I said, what's the value right there? And that's at, I don't know, x is plus 1 or something, and y is still minus 1.5. How would those two compare? Yes. What I'm trying to get across here is look at your function and try to get a visual image of how it's changing, and it's only varying in y. It doesn't change across x. So it's kind of like at any one kind of line across here at a constant value of y, the charge is the same. So it's only changing as you go this way. Yeah. Yeah. You could simplify this in a number of ways. For instance, you could just look at this and immediately do the x one. So what would the x integral be? Which is kind of what you're saying, I think. So, which is? Yep. So you could just say 6 is the x integral, right? So to slow that down in case you didn't catch it, if we're looking at the x integral, there's the only x in here is dx. When we take that integral, it's just x. Plug in the top limit of integration, 3, minus the bottom limit of integration plugged in, which is minus 3. So we have 3 minus 3. We get 6. 6 times 4 is 24. So we can bring that out front. Just say this whole thing is 24 integral minus 3 to 3 of y squared dy. Okay, what's the integral for y squared dy? Y cubed over 3. The over 3 is going to go to 24 over 3. So that's going to be 8y cubed evaluated from minus 3 to 3. So it'd be 3 cubed minus 3 cubed times 8. And I think if you plug that in, you'd get 432. And what would your units be? Yes. So we didn't mention it, but rho s was given as microcoulombs. If you wanted to be on the safe side, you could have right here written times 10 to the minus 6. That 10 to the minus 6 would have carried all the way through and been here. Or you can just remember that it's microcoulombs, so the final answer is going to be in microcoulombs. It should be. Yeah, yeah. And if it's not, you feel free to ask. Yeah. It's the total charge. So this one's per meter squared, but the total answer is the entire charge over the entire plate. So it's just the coulombs. Yep. Last one, we've only got 4 minutes, so we might not get all the way through it, but we'll get started on it. We've got a volume charge. It's a spherical shell centered at the origin, extends between r equals 2 centimeters and r equals 3 centimeters. It's useful if you can get some picture in your mind of what this looks like for all these types of problems. Can anyone suggest something in the real world that we see that might look something like that? Yes. Yeah. Yeah, I can't think of anything that's exactly like this because it's kind of weird how thick it is and how small it is. But if you think of maybe ping pong ball with a super thick and kind of make it a useless ping pong ball probably, but 1 centimeter thick. The radius is only 2 centimeters. And then the shell itself is 1 centimeter, okay? The volume charge density is given by this thing, rho v equals 3 r times 10 to the minus 4. I would immediately start to think, what does that really mean? And you'd go, okay, first of all, the volume charge only depends on r, which means the distance away from the origin. The further I am away from the origin, in other words, when I'm approaching 3 centimeters, the rho v is a lot bigger than when I'm at the beginning of the shell at 2 centimeters, okay? Rho v, v for volume, rho for charge density, units coulombs per meter squared. That should all be like, okay, this makes sense. Like it checks out. We want to find the total charge. And so we'd go to our equation. We would use this one. So we'd go Q equals the volume integral of rho v dv, okay? Okay, so let's break it down a little bit here. What's our DV? Think about this for a second before you say it. I want you to think about it. What coordinate system are we in? Spherical. How would we know that? Well, it does say it's a spherical shell. Also, it's giving us capital R's. Capital R is spherical coordinate system. Lowercase r is cylindrical coordinate system. All right, what's our DV? Say that again. So that's what you might think. Do you remember when we did our so close, very close. Yes, your head is in the right place. It's r squared sine theta and then dr d theta d phi. You remember when we introduced the spherical coordinate system and I said, this is going to come up later and you're going to be like, where did the r squared and the sine theta come from and all this stuff? Spherical coordinate system, this is the DV. The DV is r squared sine theta dr d theta d phi. Why is it that again? Well, as a basic reason, remember we're doing a DV, we're doing length times width times height. The lengths in some cases are arcs. In order to get the length of the arc, we had to multiply the angle, the d theta or the d phi, by the radius. We had to do that for two different directions because there's a d theta and a d phi. And the length of the one arc depends on where you are along the z-axis. That's where the sine theta comes from. You can also just have this table on your formula sheet. Okay. All right, it's 6:45. When we come back on Wednesday, I'll just pick up right here and we'll finish this one off, okay? All right, have a good evening.